Welcome everybody. We start off, as Sayos already said, this intermediate training event with basically an introduction to MPI, the message passing interface, and also combining this with OpenMP, which is what we refer to as hybrid programming. So for the these slides I will use for the remainder of the day. This will be there will be a lot of hands-on during this day. So I think I will probably take about an hour to present some introductory stuff through these slides, and then for the remainder of the day, we have something like 10 small exercises to practice a few of the concepts that we will see here. So I assume for this course that you are familiar with OpenMP, at least as covered in the first training event, that you are familiar with logging into the system, as that was covered again in the first training event, and submitting jobs through the scheduler, and some basic bash scripting. And the other thing I want to say is that the examples that we will look at will be in the C programming language, but you won't really need to write a lot of C. You mostly need to read some programs and modify them a bit. Okay, so this is the outline of the talk as regards the MPI introduction, and what is not listed here is some things we will see towards the end of the day on combining with OpenMP. So I will give you a very short overview of this message of MPI, the message passing interface, and just introduce some basic concepts of what we call the distributed memory paradigm, which is compared to the shared memory paradigm, which you saw so far with OpenMP. A bit about how to start up and initialize using MPI. And then we will look at three kinds of communications that one can do using MPI, which is synchronization, so-called collective operations, and point-to-point communications. And we will look at some indicative examples of functionality of these three in our exercises. Okay. So when talking about MPI, at least in the introduction, I will be contrasting it a bit to OpenMP, which you might be more familiar with. So MPI is, well, it's an API, right, in the computer science sense. So it's a library specification. So the library specifies functions, their names and arguments, and their functionality. This is a bit more different to what you saw with OpenMP, right? Where this is more pragma-based. So you basically, how should we say, decorate your code with some instructions, and then these are translated into, well, in the background, these are translated into functions, but the user-facing, let's say, interface to OpenMP is that this is it's not really like a library. MPI is a library, so there's a functions that you call to do the communication, and it is a de facto standard for programming distributed memory systems. And I'll say a bit what this means. It's a bit more in the next slides. Okay, just for your information, the current specification is MPI 3.1. This is already more than 5 years old, and there's a new version coming up, but most things have not changed, only some details. There's a release candidate for MPI 4 as of November 2020. So as we said, MPI is a is a specification. So that means that there are multiple implementations of MPI. Some are open, such as MV-API-CH, OpenMPI. So I'm mentioning this not that it's very important, but just because you might see references to either MV-API-CH or OpenMPI in like modules, and just so you know what the differences are. So all these Intel MPI are implementations of MPI. So they just, somebody else wrote a library based on this specification each time. And so that's why they have different names. Intel, for example, has its own implementation of MPI, which presumably might have some optimization specific to their systems. So distributed memory programming, as opposed to what I again say, I assume that you already did in the first iteration of this training program. So distributed versus shared memory. So in distributed memory programming, each process has its own memory domain. And then MPI, what MPI facilitates is obtaining, first of all, environment information about the running process. For example, what is the unique identifier of the process that is running? How many are the total number of processes in the pool of processes that are running, etc. But more importantly, what MPI does is achieve communication between processes, which means either synchronization or copying of data between these distinct memory domains. So just maybe it's easier to see this in the picture. So what you've probably been programming so far is an architecture that looks a little bit like this. So if you go on one node of our system, then on this node you have multiple cores, something like 40 cores. These cores have their own cache. It's not very important, but there's also a common cache. But what is important is that all these cores see the same memory, the same RAM, right? So multiple processes share the common memory. We say they have a common memory address space. An example of this is, for example, a multi-core CPU, as we said, or maybe many processes on the same node. GPU threads see the same memory, so that's another example of a shared memory system. And then there are multiple ways to program these kind of architectures. You can use OpenMP, as you learned last time. You can use so-called POSIX threads, P threads, at a bit lower level. You can also use MPI to program a system like this, but you're not really using it in a shared memory model. But that's just to say that this doesn't exclude using what we're going to learn for programming these kind of systems. CUDA, sort of, CUDA, which you use to program GPUs, is sort of a shared memory paradigm. Okay, and then if I take this picture now and try to draw what a distributed memory system is. So then I have to draw multiple nodes. Okay, and now you see that each node now, there's distinct memory address for these cores and distinct memories. Examples of this distributed memory paradigm would be, as we said, multiple nodes within a cluster, which is drawn here, or maybe multiple GPUs within a node, which have their own memory address. And basically, the way to program these efficiently, the communication between these memories is basically MPI, which we're going to learn. So in the shared memory approach, coming back to this one here, communication is achieved sort of implicitly, right? So if you have two cores, they can read the same memory address, and that way they sort of share this data, which is here, basically by going through access to RAM. So when these two cores need to share common data, this is done sort of in a very implicit way through the memory. Whereas if you have this distributed memory architecture here with the nodes with a separate memory address, exchanging data, so communicating, needs explicit communications so that data goes from one memory address to the other. And this requires going over, for example, a network. And this is what MPI achieves. It has specific functions that will take arguments so that you can facilitate moving data over a network. Okay. By the way, you can feel free to stop me and ask questions if you want to at any point. I don't think I can see hands being raised, so because my screen is because I have this.
If there's something coming up, I'll let you know.
Okay, thank you. Okay, so how do we run a parallel program? So I'm going to get a bit very simplistic here, but in Linux, it's trivial to run a program in parallel. Let's say you're on the front end node of a supercomputer like the one that we're going to run our exercises on, and you want to run the same program on 3 nodes, then this you can trivially do just by saying, SSH node 1, my program, and then you put an ampersand, so that goes into the background. And so these 3 instances of my program will run on the node with hostname node 01, on the node with hostname node 02, and the node with hostname node 03. Of course, they're just running in parallel, and they will just run identically. So I am running them in parallel, but there's no functionality to facilitate any communication when I do this. An MPI program is run in a similar way, but this is wrapped in an MPI wrapper launcher script that will also initialize the parallel environment. So things like environment variables, initializing the network, etc. So that as these three in this case instances of the program run on these 3 nodes, there's also information about the network that they can use to communicate with each other. So this program that we will use is called MPI run. So it's a script which basically you specify something. In this case, I'm specifying the nodes that I want to run this program on. And then at some point in the script, something like this will happen, but also other stuff is happening in the scripts, as I said, like setting of environment variables or initializing the network. So in practice, you actually run this MPI run command inside a scheduler script, a Slurm script, which I hope you remember from last time, where you've already determined which nodes you're going to use and how many processes, etc. So you don't really need to, most of the time, we won't really need to specify explicitly which nodes you're going to run on, but you already set that environment and you just say MPI run and your program, and hopefully the system is uniquely specified which nodes you run on, etc. So as I said, we'll be using this MPI run script, but depending on the system, you might see this. You might see people using not MPI run, but MPI exec. It's basically a synonym. Well, it's not exactly a synonym. It's similar functionality, but slightly different way you set the arguments. It just depends on the MPI implementation, whether you use MPI run or MPI exec. Some systems allow you also to use the so-called srun command. Again, this is not very important. It's just if you see people using MPI exec instead of MPI run or srun instead of MPI run, just remember it's just a similar thing. Okay, so as we said, MPI is a library. So you write your program, you write your you call your MPI functions in there. These are all in C. These are all included. These function definitions are all included in a single header file. So you must include this MPI.h include file at the top of your MPI program, or any file, any part of your source code which will call MPI commands. And when you compile your C program, just like any other library, you need to link against MPI, right? So somewhere on the system, not necessarily what I wrote here, but somewhere on the system, you need this libMPI resides, and so you need to compile your program like you usually do in C by including these. I mean, for a library, you would have to do this, but thankfully, MPI implementations come with another wrapper script, so that you don't need to specify all this stuff yourselves, but rather you use MPI-ICC instead of GCC or CC or whatever the compiler is. You use MPI-ICC, which includes this all the necessary command line arguments you need to include to your compiler, so that you can just run it as if it's another compiler. Okay. And these also exist for Fortran and for C++ in a common MPI installation. Okay, so let's look a bit more in detail about look at some MPI functions. So first of all MPI functions begin with this prefix in C. In C++, this is a namespace, but we won't be looking at C++ today. We'll be looking at C, and so basically just the function names are prepended with this MPI underscore. And the first function you should ever call before calling any other MPI function is MPI init, and to MPI init, you always pass the command line arguments here. We'll see a specific example if you're not sure what this means. And before the end of the program, so before your main function returns, you should call MPI finalize. MPI finalize cleans up the environment and everything. But apart from that, you want to call MPI finalize because usually the MPI runtime environment might assume your program finished with an error if you don't call MPI finalize before. Okay, so it might think that basically your program exited in error if you don't call MPI finalize at the end. So that's a bit annoying. So you should always use MPI finalize before you return your main function. So
Can I ask? Marco asks if it is like dynamic or static compiling as in Fortran. Marco, can you ask the question more?
So what I wrote here.
Yeah.
Well, here this is static linking, but I just did this as an example. I don't really. I think it depends whether. What you can do is you can look at what MPI-ICC is actually doing and figure out if it's dynamically linking or statically linking. I think most of the times it's statically linking. So it'll do something like this. but probably there are options to also make it dynamically linked. Did that answer the question? I don't know.
Yes,
what was that the question?
Yes, okay. It was. Thank you.
Okay, so I just wanted to show you here, just this is more of a cartoon rather than anything else. So we start, as we said, just to wrap up what we said, a very not even hello world example of an MPI program. So include your header file MPI.h. This is just standard what we do in C. This is the number of command line arguments, and the command line arguments has a string array. You call MPI init, passing argc and argv to it. Then you call do interesting stuff in here, which I've commented out, and then you call MPI finalize. Okay. And then, so everything, all the examples we will look at that follow start this way. And then we will have some examples where I've omitted here with the ellipses. Okay, so the two functions you will almost always call when you're running an MPI program is MPI com size, which this gives the number of parallel processes that are running in this pool, and MPI com rank, which determines the rank of the process. So that's basically the ID of the process, which is a unique number which starts from 0. Okay, so the first process is processed with the rank 0, and the last process is processed with rank number of processes -1. Okay, so this is a complete example now, which will initialize and will call MPI com size and MPI com rank, and will print to the screen, this is rank whatever of n processes, how many processes you ran. So this function will return the same for all the processes in the pool. So all processes will get the same value of nproc, hopefully, otherwise it's wrong. But every process will get a unique return value for rank. Okay. So all processes should give the same number for nproc when they print, and all processes should give a unique rank when they print. I should say what this MPI com world thing is here. So the type of this variable that I put here is an MPI communicator, and an MPI communicator is basically it's a variable that specifies a grouping of your processes. When you call MPI init, this default communicator is always defined, called MPI com world. It's a constant basically defined in MPI.h, and this MPI com world specifies all processes, right? So it's a shorthand for all processes, and it's always available for you. As you become experts in MPI, you can do fancier things, and you can define your own communicators and partition the processes into, I don't know, even ranked, odd ranks, or color them, or I don't know. But we won't cover this here, okay? So we will always use MPI com world, which means all processes when we talk about MPI communicators. All right, so let's think about, so if you would write this program, you would put it in a .c file, you use MPI-ICC to compile it, right? And then you go and run it. So I'm stepping back a bit to go to the previous slide. So you might run it here we are. So you might run it like this. You might call it my MPI program. You compiled it with MPI-ICC, as I said, and then you run it in MPI run. Let's say this runs now on 3 nodes. So like you did here, okay? Then so then what's being done? So node 1 takes this program, runs it. Node 2 takes the program, runs it. And at some point they reach this function, MPI size. So they will get the number 3, right? They will get the number 3. And then they will reach this function, MPI rank. So let's say the process on node 1 gets 0, the process on node 2 gets the number 1 for rank, and the process on node 3 gets number 2. And then you go and say printf here, and then they print. So you can make no assumptions, right? There's no safe assumption to make about the order in which the printf statements will occur, right? Because there is no synchronization here. They basically run as independent programs after MPI init, between MPI init and MPI finalize. So the order in which the processes will print will be practically random, undetermined, right? So it's just an example here. So here I run it on 5 processes. I called it example here. And so you will see every time you run it, basically you probably get a different order. So the first function we will look at is the so-called barrier function, which basically solves this problem if you need to solve it, which achieves synchronization between processes. Well, the way this works is that all processes must call this barrier function. And then for any process to exit the barrier, all other processes must have entered the barrier first, okay? So as an example, so you run an MPI program like this, my MPI program on 3 nodes. And somewhere in this program, there's a barrier, which is somewhere I've represented with this dashed line. And as I said, there's operating system noise. There's all sorts of reasons why, you cannot deterministically say that these 3 processes will run at the same pace in parallel, right? So these nodes are running their own operating system. They're complicated. There's services running in the background, etc. So these will never be these 3 programs running in parallel are never guaranteed to be exactly at the same point. So, for example, node 2 might get ahead, and then it hits the barrier. So basically, what that means is it stays in the barrier until, well, then node 1 reaches and node 3 reaches. And only once all these 3 processes have called the same barrier is any of them allowed to sort of emerge from the barrier. And then again, they might lose sync, and you might need to have another barrier if you need to synchronize them, right? So that's sort of how this barrier works. And we will be looking in the examples at a way how to use this to synchronize processes when you need to. All right, so that's the first and most simple function that we learned, MPI barrier. And as I said, we will look at it a bit more in the exercises. That brings me to the next class of MPI functionality that I want to talk about, which is so-called collective operations, okay? So collective means that all processes must be involved in the operation. This is different from so-called point-to-point communications, which we will see later on. So these are examples of collective operations, but this list is not exhaustive, but they are functions that we will look at also in examples that will follow. So maybe the simplest collective operation is a so-called broadcast operation, in which I think it's simple from the name. A variable or a set of variables is broadcast from one process to all processes, okay? So you have a single process having a value for a variable and you want that to be copied over to all the participating processes, you would use the so-called broadcast operation. Then there is a scatter operation, and the scatter means distribute elements of an array on one process to multiple processes. So sort of take a big array and distribute pieces of that to all other processes. And then the gather operation is the inverse of the scatter, in which you basically collect elements of arrays scattered over processes into a single process. And then the last collective operation that we will look at is so-called reduction operation, where a variable is reduced over processes. Okay, so that can either mean that you sum the variable over processes, as I wrote here, or you could do something like the product of variables over processes, etc. You can do logical operations of variables over processes, like take the OR of a variable over process, etc. So, excuse me, just to look at a bit of a pictorially how this works. So say you have 3 processes, just for the sake of easing the pictures here. So you have the root process 0, and the root process has a 4-element array, and then it would use a broadcast if it wants the values of this array to go into this processes 1 array and processes 2 array, right? So it's a broadcast, so it sends the same data to all processes. Okay, that's a bit trivial. So the scatter operation is a bit less so trivial. So so now I've renamed this array into SR, for short for send array, right? So you have now 6 elements of this array, okay? And you have 3 processes, and note that process 0 also participates in the receiving end, right? So it's both the sender and also receives its share. So as we will see, you need to specify a send array, as I did here, but you also need to specify a receiving array. And in this case, if you have 3 processes and you have 6 elements in the array, then what you likely want to do is send 2 elements to each process. And so this is how that would look like once you finish the scatter operation. And then, as we said, the gather operation is the inverse of that, where you would start off in a situation like this, where you have 2 elements of a send array on each process, and then you want to gather them in some process. In this case, it's process 0, and fill up a receive array, which is 2 times 3, 6 elements long. Okay. And the reduction we will look at a bit more in a few slides. Okay, so now I'll go and show you some examples one by one of each one of these. Okay, so that we're also a bit prepared for the exercises. So this is what the call signature of the broadcast operation looks like. So first you specify what you want to broadcast. So if I step back here, that would be this array here of 4 elements. So this is the buffer that you want to send, and the number of elements in the buffer and their type, right? I'll explain what this type means in this slide following, but root is where the data will be copied from. So in this case, root would be process 0. So it's root is a rank. Here it's expecting a rank. And then com is this communicator I talked about. And as I said, we will just use MPI com world. If you have your own custom communicator, then you can specify a custom communicator so that this buffer is broadcast to, so let's say, a subset of ranks, but that we won't cover, as I said. Okay, so here is an example. Broadcast from rank 0. The 4-element double precision array are Okay, so that's how that would look like. MPI bcast are, I have 4 elements. This MPI double is a data type. It's an MPI data type. I'll say a bit more about this. 0, as we said, is the root process, so where to copy from. And then MPI world is the communicator. Broadcast from rank 0, which is the root process, the scalar integer variable var, right? So if you want to send a scalar variable, then you need a pointer you need to send the pointer to that variable, because as you see, the core signature here says that you specify a pointer to the data that you want to send. Then you will specify that this is just one element. The data type is MPI int, and then again from the root process 0 to 1. Okay, so the MPI data type is important in this case because MPI uses it to estimate the size and bytes that need to be transferred, okay? So MPI in the background, so this MPI bcast command will take 4 and then say, okay, I have 4 elements of something which is MPI double. So that means I need to send 4 times 8, 32 bytes of this array, okay? And in this case, it will say, okay, I have an MPI int. So this is 4 bytes, 1 element. So I need to send 4 bytes of this var, need to broadcast 4 bytes of this var. So this data type here is important, it's what it says here. I'm not repeating it because MPI will use this to calculate how many bytes to send. Right? Now, there's a full list of types available in MPI documentation. This is an example here. By the way, what I don't think I gave Stelios the slides, right? So is it okay if I put the slides in the Slack?
Yeah, you can send it to me. Well, put it in Slack and I'll put it online now as well.
So it's a PDF.
Yeah,
Slack.
that's fine. If you send it me or put it on Slack, and it'll be online within the next few minutes. No, well, by 11.
Yeah, I just remembered because I put this link here, which people might want to hit. So this is just an example, right? So this is for the case of MPI-CH, where you document the data types and the constants that one can use. But the names are pretty obvious, right? MPI float will be for single precision, MPI double is for double precision, MPI int, MPI char for a character, etc. Good. Let me go back to that. Yeah. Okay, so that's MPI broadcast and some examples. I might be going a bit fast now, but we will spend more time on each one of these in the examples, okay? So the next collective operation we said is this scatter operation, in which, as we said, you take an array and you distribute it. So the core signature is this. So you specify first what you want to send, how many elements you want to send, and its data type. And then you specify in which array you want to receive this, how many elements you want to receive, and of which data type. And then, of course, you specify the route. So from where should this send buffer be read, and the communicator. So send count is the number of elements to be sent to each process, okay? So in this specific example that I had back here, so send count in this case would be 2, and receive count would be 2, okay? So it's the number of elements to be sent to each process. It's just the convention. And then the send buffer, right? So what is to be sent is only relevant in the root process. So it doesn't matter if other processes can have anything here, it won't be used. So for example, distribute a 12-element array from process 0, assuming you have 3 processes in total, including the root. Okay, so 12-element array, you have 3 processes, so you want to send to each process 4 elements. So first you have the array that you're going to send. So I'm just defining it like that here, R all. Then you have the array per process, R proc. And then imagine that R all is filled somewhere between this line and the next line, so that it has some useful data, and how you want to distribute it. So all processes will call this, right? But this rank here, this 0 that you put here, specifies that the data that will be sent from process 0, 4 elements, MPI double, put it in R proc, again, 4 elements, MPI double. Okay. It might seem strange to you that we're repeating 4 elements MPI double and 4 elements MPI double from the sender and the receiver. So you might be thinking to yourselves, justifiably, isn't this unique? So if I specify that I need to send 4 elements of MPI double, isn't it obvious that on the other end they should receive 4 elements of MPI double? Well, there's multiple reasons why you would have to specify it on the sender side and on the receiver side. One interesting one, and it might sound a bit obscure to you now, but I should say that you can define custom data types in MPI. We won't see this here. This is a sort of advanced topic, but you can define custom data types in MPI, which also have gaps in them. So that if you want to send these 4 elements of an MPI double, and that they land in 4, let's say, non-continuous elements of the array on the other side, then you could have a custom type here which specifies that. And then you could define, you would have something different here on the receiving side than on the sender side, okay? So there is a reason why, that's just to say that there is a good reason why you need to specify both the send count and send type, and that it can be different from the receive count and receive type, okay? Good, here's another example. Distribute each element of a 4 element array to 4 processes, okay? So now you have an array which has 4 elements, and then you just want each process, we have 4 processes, each process to just get 1 scalar variable. So the receive buffer it needs to be a pointer, in this case, a pointer to a variable. So that's why you would specify it like this with an ampersand in front of this element variable, because you want to specify the pointer to the other. Everything else is the same. I'm going to send 1 element to each MPI double, and I'm going to receive 1 element in each MPI double. Good. So that's the scatter operation. And the next one is the gather operation. We will see. MPI gather. Again, this looks a lot like the scatter, only that the no, this looks no, that's what I'm saying. This looks a lot like the core signature. Looks a lot like the scatter operation, right? Almost identical. You have send buffer, send count, receive buffer, receive count, and the root process and the data types. So again, in this case, receive count is the number of elements to be received by each process. Okay. So if I go back to this picture again here. So here, receive count would be 2, not 6. Gather. What else do I want to say here? Again, this receive buffer is only relevant in the root process. So if the other processes do not allocate, for example, space for this receive buffer, this won't be an error. And here's an example: collect a 9-element array at process 0 by concatenating 3 elements from each of 3 processes in total, okay? So each process has this 3-element array, and you want to collect them all in the root process, collect into a 9-element array, then you would define it like this, okay? So First, you specify the send buffer, the number of elements that you're going to send for each process, precision, and then again where it will land in the root process. And just an example again here with a scalar, with an example with a scalar argument, just to show that if you have a scalar argument, then you again need to put the ampersand in front because this takes a pointer to the array. Okay, good. And so the last thing we do now is the reduction, and then maybe we stop and then do some exercises after the break. Okay, so the reduction operation looks like this. Before I talk about the arguments, maybe I should show you a bit the picture here. So basically what you have is you have some arrays on the processes, and you want to, as we said, reduce the values into the root process by applying an operation. So this operation might be an addition, it might be a multiplication, you might want to multiply the elements, etc. So in this case, you have a 2-element array on each process, and you want to end up with a 2-element array on process 0. And for example, you would want the first element of the reduced array on process 0 to be the sum of the first elements of this array on all processes, and the second element to be the sum of the second elements. So you need to specify in the MPI reduced, this core signature has the send buffer, right? So what is the address of the array that you want to send, you want to reduce, and the receive buffer, which in this case will be the reduced array here, the number of elements and their data type. And now, of course, the data type has to be the same. You only specified once, because if you're going to do an operation on them, then of course they have to be the same data type on the receiver and the sender. Then this operation here is an MPI-op type, and then you specify the root process, which is where the actual reduced array should reside after the operation and the communicator. So as I said, MPI-op is an operation. It could be MPI-sum, MPI-prod, MPI-or, etc. You can find the full list in the documentation. And here now, the data type is not only important for specifying the size of bytes that will be sent and received, but the data type is also important because you want the operation to be valid for that data type, right? So if you're gonna do a sum and you specify int, but your buffers are double, then you will get the wrong result, right? So count is the number of elements of the arrays, and is the same for the sender and the receiver. So in this case, count will be 2. And again, the operations overall process in COM. And so if I would write, oh, I'm sorry, I'm confusing you here by using different names. So this does not correspond to the picture. What I wrote here, it corresponds to summing a 3-element array over processes. So this is the send array. So this will only be, this only needs to be defined on the root process, this R array, the reduced array. Then you would say 3 elements, double MPI sum, roots 0, and MPI compiled. So if you have a scalar variable again, so you don't have an array, some scalar variable over processes, so you have something like this, then you would specify the pointers to both var and sum in the MPI reduce, and then you would have 1 element. Okay, so that's our introduction to collective operations. And before I go on, I just want to maybe talk a bit about some additional notes on variance of these collectives that we won't cover, but just so that you have in mind. Just like MPI scatter and MPI gather, there are these V versions of them which end with a V. And these allow specifying varying number of elements to be distributed or collected to or from the process pool, right? So what we've seen so far is you distribute the same number of elements from the array or gather the same number of elements. These V versions of scatter and gather allow specifying a varying number of elements. And of course, they have additional sets of arguments that you need to specify to do this. There's a variant of reduce, which is called MPI all reduce, which is the same as MPI reduce, but the result is placed on all processes in the pool and not just the root process. So the result of this operation is equivalent to doing MPI reduce followed by broadcast of the sum, right? The result is equivalent. Maybe all reduce is more efficient than doing this. And then another thing that I want to talk about that we won't really see, but maybe it's good to have in mind, is that some of these functions allow for so-called in-place operations. So for some of these functions, you can replace the send or receive buffer with this special variable MPI in place. It depends on the function whether you will replace the receive or the send or the receive buffer. But what this does is it instructs MPI to use the same buffer for receive and send, right? So, so for example, if you want to sum this variable over all processes and have the sum end up in the variable itself, then you could do something like this, where in the root process, you specify MPI in place. And so in the root process, the result overrides the input. Okay, I'm going to stop here. And then we can continue after the break with some examples of these collective operations. But before I do that, I need you all to log into the cluster. So have you all logged into the cluster?
So maybe somebody who hasn't logged in, please speak now.
So let me. Okay, let's see. So okay. So can you see that? Is it big enough?
I think yes.
Okay, so sorry, I shouldn't have done something. Anyway, I'll fix that during the break. So oh, don't worry about this crap. So you want to do something like this. So this is my educational username, edu12, my initials 1. You should have gotten something similar. At cyclone.hpcf.cy. I already have you might be prompted for your SSH key password. And this should, if you're logged in, you should see the message of the day message here, so that you're sure you're actually on Cyclone. And your home directory should just have some symbolic links to data directories. Okay, so you should be able to be here when we start after the break. If you don't, then you need to speak up.
Okay, well, let's go for a break now. We're due to start at 11:30. So please be on time. Please be already able to begin at 11:30. So join or get to your desks or in front of your computer at 11:27, let's say. And please, before you do that or during the break, make sure that you can log into the system as Yanis just showed, and so that we're able to begin with hands-on sessions at 11:30. So yeah, go ahead for a break now, and then we'll talk again in half an hour. But please let us know if you have issues with logging in. Thank you.
So I'll stop sharing the screen now, or do you? And then, yeah,
you can if you want.
Yeah, I think I'm going to stop sharing the screen, and then will that affect the recording?